Hello friends. So in today's lecture, we will be looking at developing flows. We actually mentioned about this in the previous class, that we in the last class also we were actually looking at thermally fully developed flows, but in dealing with that, we actually talked about flows where we don't consider the velocity profile development. We consider that the velocity profile is already fully developed right from the beginning of your region of interest. So we were looking at how much distance would the thermal boundary layer take in order to make the flow fully developed. So we were looking at the expression for the thermal entry length, given that the velocity profile has already fully developed. And then we went on to discuss how fully developed flows, thermally fully developed flows behave. So we understood that thermally fully developed flows basically means that the non-dimensional velocity profile, which is scaled by T wall minus T mean, becomes invariant with X, and in other words, the heat transfer coefficient H becomes invariant with X. So that is what we looked at in the last class. So in this class, we will just look at one of the implications of the constant H behavior of the fully developed flow in terms of calculating the overall heat transfer rate through a pipe with constant wall temperature if the flow is fully developed in the entire length. Then we will also look at what would be the way in which Nusselt number would vary with X in the developing region. And then we will look at a glance of or glimpse of how thermally developing flows can be solved for. In fact, what we will find is that analytical solution is only possible for a restricted class of problems, but for the more general case of developing flow, which will be basically if I have a pipe into which the flow is also coming in with a flat velocity profile and the temperature uniform Ti, and then there is a, let's say, constant wall temperature or constant wall flux boundary condition, the velocity profile is also developing, the temperature profile is also developing. For such cases, which is the most generic case of developing flow, no analytical solution would be feasible, and therefore closed form expressions for Nusselt number would not be feasible. So we'll need to go for numerical solution of such problems. So we will give some results of what kind of results are actually available in literature for such problems. So that is what we will be doing in today's class. So let's move to the whiteboard and start discussing about first the fully developed flow with constant wall temperature, the calculation of overall heat transfer. Okay. Overall heat transfer in fully developed flow with constant wall temperature. So we said that in this kind of flows, if I look at the variation with X of temperatures, the T wall would remain constant and the T mean would approach this exponentially asymptotically. This is something that we can actually derive from the expression that we wrote by taking a elemental segment of a pipe in which the flow is going. So let's say the T mean this location is Tm, and here it is Tm plus dTm over a distance dx, in which there is a wall flux Q wall that's coming in. Okay, there is nothing said about whether Q1 is constant or T1 is constant or both are variable. Let's take the most general case. So in which we can actually write that if m dot is the mass flow rate through the pipe into Cp multiplied by dTm, that is the change in temperature. This happens because of the heat transfer that is happening, which is Q dot double prime at the wall multiplied by the perimeter into X. Okay, so this is what we had written. So if I expand this, m dot would actually become rho u bar into area. Okay, so if I write this whole expression, I get dTm by dx is equal to Q dot double prime wall divided by rho u bar Cp multiplied by perimeter divided by area into the perimeter by area. So this is your expression. So if it is for a circular pipe, okay, if it is for a circular pipe, then perimeter is pi d or 2 pi r naught, and area is pi r naught square. So perimeter by area will actually be 2 by r naught, right? So that is the expression 2 pi r naught divided by pi r square. The pi would get cancelled, you get 2 by r. So this I can write it as is equal to Q dot double prime into 2 divided by rho u bar Cp bar. Okay, so this is the expression that we would get. And if I write this Q wall as H into T wall minus T mean, okay, this is a general expression. And in the fully developed region, this H is a constant, and in the case of constant wall temperature, this T wall is also a constant. Okay, so now let us apply this general result to the problem of constant wall temperature in fully developed flow. So if I do that, then in fully developed flow, H is constant, and for constant T wall condition, we can write d by dx of T mean minus T wall, because T wall is a constant, subtracting it will not change the left hand side. This will be equal to H, this is a constant, divided by rho u bar Cp into R naught, right? And this multiplied by T wall minus T mean, right? Did I miss anything? There is a 2 there. So if I try to integrate this expression, this is a T mean minus T wall, this is a T wall minus T mean. So if I bring it to the left hand side, I'll get a d of T mean minus T wall divided by T mean minus T wall is equal to, the minus sign will go here, so minus 2H divided by rho u bar Cp to R naught, right? So this is the expression multiplied by dx. Now if I integrate this from a point where the velocity profile is already fully developed to this one, so if I say that at the inlet itself the velocity profile is already fully developed, so I can say T mean at the inlet and T mean at the outlet. These are the mean temperatures at the inlet and outlet of the pipe where the velocity is fully developed. So then if I integrate this from inlet to the outlet of the pipe, this from inlet to the outlet of the pipe, okay, so then what do I get? I get log of T mean I minus T wall by T mean O, T mean O minus T wall divided by T mean I minus T wall is the expression that you get on the left hand side, and this will be equal to minus 2h divided by rho u bar Cp r naught, this is a constant, multiplied by the length of the pipe. Okay, so this is your expression that you would get. And we also know that the total heat transfer Q dot is going to be equal to m dot Cp into Tmo minus Tmi. This is the total heat transfer that has happened through this pipe. And this m dot, I can write it as rho u bar Cp into rho u bar into pi r square. Okay. So this is the expression. So if I write Q dot is equal to rho u bar into pi r naught square into Cp multiplied by Tmo minus Tmi. Okay, and this will be equal to, I know that rho u bar Cp r naught is already there. So if I take this to the left hand side and bring this to the denominator here, then I'll be able to write, and this minus sign can be absorbed into this expression. Okay, so then I will be able to write that this will be equal to 2HL multiplied by, there is a R naught and this is a pi R naught square, so there will be a pi R naught that I have to multiply it by, divided by the left hand side logarithm of Tmo minus T1 divided by Tmi minus T1. Okay, and multiplied by Tmi minus Tmo. Okay. Yes. So now if I rearrange this, I can forget about this side of it. If I look at this side, this 2 pi r naught will be the total heat transfer area. So H is a constant. H into area, 2 pi r naught into L is the total heat transfer area. So H into A into, this is in some sense a logarithmic mean temperature difference. So this I can actually write it as T. Okay, so this okay. So since our heat transfer happens H into T wall minus T mean is the local heat transfer area location. So let me write it in terms of T wall minus T mean. So I can multiply by minus 1 both numerator and denominator without any change in effect here. Here I can write it as T wall minus Tmo minus T wall minus Tmi. So basically I've added and subtracted T wall. This will be the value of this expression, and this can be written as log of T wall minus Tmo minus log of T wall minus Tmi. So if I write this, it actually becomes T wall minus Tmo minus T wall minus Tmi divided by log of T wall minus Tmo minus log of T wall minus Tmi. So this becomes a certain log mean temperature difference. So I'll be able to write this as Q dot is equal to H into the total heat transfer area 2 pi r naught L multiplied by delta T log mean, where delta T log mean is actually equal to T wall minus Tm O minus T wall minus Tmi divided by log of T wall minus Tmo minus log of T wall minus Tmi. Okay, so this is your so this is the temperature difference outlet, this is temperature difference of the inlet, this is temperature difference outlet, temperature difference inlet. So if you want, these minus signs can also be reversed. So the outlet can be brought this side here as well as here without any loss of information. So that is the way the temperature difference at inlet minus temperature difference at outlet divided by log of temperature difference at inlet minus log of temperature difference at outlet. So that is your delta TLM, and based on that you get the expression for the total heat transfer. So this is something that is commonly used for heat transfer to a fluid that is heated using a constant wall temperature pipe when the flow is fully developed in the entire length. Of course, if h is not a constant, then it also becomes a function of x, which needs to be integrated along with the remainder of the expression. Then this becomes more complex. It doesn't remain this way. But this expression is valid when the flow is fully developed in the entire length, or you can assume that the developing length of the pipe can be neglected. Okay, so that is one part. The second one is variation of NUD with X in the developing region okay. So this variation of Reynolds number. So if I look at the pipe, for a moment let me assume that the velocity profile is already developed. So then there is a the thermal boundary layer that starts developing here, and at some x, which is LET, it gets fully developed. So when x is much less than LET, we can say that the mean temperature T mean is approximately equal to the inlet temperature Ti. Okay, and so if I write the expression for Reynolds number, which is h into d by k, where this h is nothing but q dot double prime divided by T wall minus T mean. In this case, it will be T wall minus Ti itself multiplied by d by k. And for a thin boundary layer, if I say this delta T is very small, then I'll be able to say that q dot double prime would be equal to k times T wall minus Ti divided by delta T. So this is of this order. So if I look at this expression, then this whole thing, the delta T is of the order of, is approximately equal to k into T wall minus Ti divided by q dot double prime wall. So if I look at this expression, it becomes equal to 1 by delta T. So I get d by delta T. Okay. And if I use the boundary layer results to get the thickness of delta T as a function of Reynolds number, then I'll be able to write NUD is d by delta T, and since delta T by x is above the order of REX PR raised to the power of minus half, so I can write this is REX PR would actually be alpha divided by u bar into x to the power of half, right? Because it's minus half, so I've just inverted this. So this is this. So if I want delta T divided by B, this would be equal to, so I'll just have to multiply it by, so this is delta T by x, so I have to get it into x by d. So if I multiply this by x by d, I'll get x by d multiplied by alpha by u bar x to the power of half. Okay. So now what I will do is to convert the Reynolds number in terms of d. So I'll multiply and divide by a square root of d. So I'll get this is equal to x to the power of half will cancel with this, so I'll get x to the power of half here, and I'll multiply and divide by square root of d. So this square root of d will actually make this as d to the power of half, and this square root of d goes inside to give me alpha divided by u bar d. Now this actually is nothing but RED PR raised to the power of minus half, right? And this is x by d. So that is the expression that I can get. So I'll be able to write this delta t by d is equal to square root of x by d divided by RED PR to the power of half. Okay, or rather this whole thing can be put in square root. Okay, so then NUD, which is of order of d by dt, d by delta t, will be the inverse of this. So this will be equal to x by d divided by RED PR. It's actually not equal to, it's of the order of x by d divided by RED PR, whole thing raised to the power of minus half. Okay, so this is one result that we will find in practically all developing flows. Okay, so we have not said anything about the boundary condition here. All we have said is that it is in location where x is much smaller than LET, so it's in the developing region. So in the entry region where the distance is quite far from, or the x is much less than the entry length for thermal flow development, then your variation would be in this form. So wherever we find developing flows plotted, you would normally find the x coordinate as x by d divided by RED PR, whole thing raised to the power of half in the x-axis, and this will be a log axis actually, and this will be another log axis in which you plot d. And what you will find is that you will find a curve which goes like this and then goes to a constant. That is not a constant, the way I have drawn it. Here it goes to a constant. Okay. So for example, for constant wall temperature, this constant value is 3.66, and constant wall flux it will be like 4.364, and so on. So depending on what problem it is, in the fully developed region it will reach that constant value, and before that this slope will be unity. There will be a -1 slope here in this region. So that is basically what you say. So if you take the log of nu is of the order of log of x by d by r x dr. Okay, so this is of the order. So with a minus sign, of course, because it's a minus half. So there is a -1 slope that will typically come. So this is the way most of your Nusselt number plots would be, and normally this number quite frequently is called it's related to a number called the Great's number. Great's, which is actually equal to pi by 4 divided by x by d by RED PR. Okay, so basically this multiplied by pi by 4 will be the Great's number. So that is usually, so in the x-axis actually it is pi by 4 Great's number. That's this is what the x-axis is usually in the log scale, and this is the this is how usually the plots are. This number has significance because of the way the Nusselt number varies. Okay. So this is basically how you expect the thermally developing flow to behave with x. So with x, there is a decreasing Nusselt number. We all understand that at the inlet there is a singularity because there is a temperature difference, finite temperature difference across zero thickness of the boundary layer, and therefore the Nusselt number or the heat transfer coefficient is infinite. And then as we go inside, as the boundary layer thickness becomes finite, then there is a 1 by x kind of variation, hyperbolic variation. In this particular case, it is 1 by x to the power of half variation that you see. Okay, so that is the expression that is shown here. Okay, so now let's move on to thermally developing Hagen-Poisson flow I hope you all are familiar with this Hagen-Poisson flow. Hagen-Poisson flow is basically flow through a capillary tube. Which basically means that U by U bar is equal to twice 1 minus R tilde square, where R tilde is R by R naught, where R naught is the radius of the pipe. So this is the velocity profile that prevails here. So that's why we called it the Hagen-Poisson flow. So thermally developing Hagen-Poisson flow is basically where in a pipe, all through the length of the pipe, I can assume that the velocity profile obeys this condition and the temperature profile is developing. So if I write the energy equation, you'll get U del T by del X plus V del T by del Y is equal to alpha times 1 by R del by del R of R del T by del R plus del square T by del X square. Okay, so we've taken constant properties throughout. In this energy equation, since the flow is the Hagen-Poisson flow, which is fully developed, V is 0 because the velocity profile is fully developed. There is no lateral movement or radial movement of the fluid, so this is 0. And we had also looked at when the flow is thermally, if we can take the case where REXPR is much greater than 1 in this direction. So the axial conduction is much less than radial conduction. Then in that case, I can neglect this term also. So axial conduction is neglected and fully developed velocity profile. So the equation has only these two terms. And I know this U would actually be 2U bar into 1 minus R tilde square. This is the velocity profile that is already known to me. Okay. So if I substitute that, then my equation would become something like 2U bar into del T by del X is equal to alpha times 1 by R del by del R of R del T by del R. Okay. So now I can non-dimensionalize this equation using theta is equal to T minus T wall divided by Ti minus T wall, where Ti is the inlet temperature, that is at x is equal to 0. Okay, that is the temperature at x is equal to 0. And I normalize x using, let's say, x tilde in the familiar way, x by d divided by Red PR. Okay, so this is my non-dimensional x, and R tilde we already know as R by R naught. Then if I, and this Red of course you know is U bar, that is average velocity multiplied by diameter in divided by U. Okay, so if I bring this alpha to this side and rearrange this expression, then I'll get sorry, this 1 minus r tilde square is missing. Okay, so now if I write in terms of these, then um, Ti minus T wall will come out of both sides and get cancelled. So I'll get a Ti minus T wall, that is normalizing this to get theta, into 2u bar into 1 minus r tilde square into, and divided by this x. If I write in terms of x tilde, it will be REDPR into D. So into D into REDPR is u bar D by nu and nu by alpha. So this becomes alpha REDPR. Okay, so this is the left hand side, that is equal to alpha times 1 by r tilde del by del r tilde into r tilde del theta, del theta by del x tilde. That's missing here. This is equal to this del theta by del r tilde. Okay, now this alpha would get cancelled between these two sides. Okay, the u bar would get cancelled between these two, and then this r tilde I'll need to get a alpha divided by r naught square, because there are two, these two r's get cancelled, these two r's, so there will be an r naught square here. So if I cancel the r naught square with this d square, I should get a 4 here. Okay, so and this also will become a Ti minus T wall, since we have written in terms of theta. So this Ti minus T wall would get cancelled between these two sides, and this would become 1 by 2, and this 1 over r square, I'll move it to this side. So all I'll have will be a half here, okay, and del theta by del x tilde, and here I'll have 1 by 1 minus r tilde square into this. So the right hand side will be entirely a function of r, and the left hand side will be entirely a function of x. So let me write that. So I get half of del theta by del x tilde is equal to 1 over 1 minus r tilde square into 1 by r tilde del by del r tilde into r tilde del theta by del r tilde. Okay, is there anything else that I missed from there? Yeah, so that is the expression. So now, since the left hand side is entirely a function of x and right hand side is entirely a function of r, it looks like there should be possibility of separating the variables. So theta can be written as a function of r alone, or r tilde alone, multiplied by a function of x tilde alone. Okay. So theta can be written as a product of capital R, which is a function only of r tilde, and capital X, which is a function only of x tilde. So if I do that, then I'll get half of since r is a constant, I'll be able to take the r out of this differentiation. It will be dx by dx tilde is equal to, on the other side, I'll have, since this theta is x into r and this x is a function only of x and it's not a function of r, I'll be able to take the x out here, divided by r tilde into 1 minus r tilde square into del by del r, or it will actually become a d by dr of r tilde dr by dr tilde. Okay, so now I can separate the variables completely. This r can go this side and this x can come this side. So I'll get a dx by 2x dx by dx tilde divided by 2x, okay, on this side will be equal to r by 1 r tilde into 1 minus r tilde square into d by dr of r tilde dr by dr. Now, since this left hand side is entirely a function of x and right hand side is entirely a function of r, both of these independently should be equal to a constant lambda square. And since this will give an exponential solution, I need to have a negative lambda square so that it's a convergent solution. Otherwise, with x, it will go on increasing. Actually, I need to get theta to go on decreasing with x. That's the trend of solution that I expect, and therefore I get a minus lambda square. So now, by separation of variables, I can solve the right hand side, this equation. This gives a Sturm level problem, and this is a simple exponential problem. So I'll be able to write theta is equal to summation over n is equal to 0 to infinity of Cn and multiplied by Rn exponent of minus lambda n x tilde lambda n square into x tilde. Okay, so that is the typical solution that you will get, where Rn is a function only of R. And it's a series solution which is convergent because lambda n would go on increasing as so the x will go on increasing as you go further, and as n increases, the terms will be convergent, and this will. So this, along with the boundary conditions that theta is equal to 1 at x is equal to 0, because theta is t minus t wall divided by ti minus t wall. So theta is equal to 1 at x is equal to 0 or x tilde equal to 0, and theta is equal to 0 at r tilde equal to 1, that is t equal to t wall, and del theta by del r equal to 0 at r tilde equal to 0. With these boundary conditions, you should be able to evaluate and get these numbers, and you get an analytical solution. Okay. So with this, then I'll quickly write down the solutions that you typically have. You define another function g, which combines the c and r. So you define gn, which is minus cn by 2 into rn prime at 1. Okay, so if I define that as the function g, then I should be able to write the solutions in terms of g. So I'll be able to write theta mean, which I integrate the temperature, and I get this, which is Tm minus T wall divided by Ti minus T wall. This ends up becoming equal to, so that Tm is defined usually in the usual way. Tm is equal to integral of u T dA divided by integral of u dA over the area. Okay, so if you define this actually gives you 8 times summation over n is equal to 0 to infinity of gn by lambda n square multiplied by exponent of minus 2 lambda n square into x tilde. So that is your mean temperature at any x. Okay, so this is entirely independent of radius. It only gives you a function of x. So that is your theta mean, and you should be able to write NUD, which actually is defined from the derivative of this one. So you write that r tilde equal to 1. You write h into t wall minus t mean is equal to k times minus k times del t by del r, at r is equal to 1, r is equal to r naught. Now, if I write this in terms of non-dimensional things and use theta m and all that and simplify, you get an expression for NUD, which will be h into d by k. Okay, so this is h d by k at any x. Okay, this will give me an expression which looks more like summation n is equal to 0 to infinity of gn into exponent of minus 2 lambda n square x tilde divided by summation n is equal to 0 to infinity gn by lambda n square exponent of minus 2 lambda n square x tilde. Okay, so this is the expression that you get for NUD, so which is written as a function of x. Okay, so this is called the Grace series solution. And the various eigenvalues gn and lambda n, various eigenvalues lambda n and the corresponding eigenfunctions gn can be found. So they have been tabulated in the literature, so you can use that. In place of this Grace series solution, there is also a slightly more approximate solution called the Levick solution, which was basically obtained by evaluating this series and then fitting it to simpler functions. So for T1 is equal to constant, the Levick series solution looks like this. NUX is equal to 1.077 x tilde raised to the power of minus 1 by 3 okay, minus 0.7 for x tilde lesser or equal to 0.01, and this should be equal to 3.66, which you recognize as the fully developed Nusselt number, plus 6.874 into 10 to the power of 3 x tilde whole thing raised to the power of minus 0.488 into exponent of minus 57.2 into x tilde. This is for x tilde greater than 0.01. Okay. So this is in a simplified fashion how you can evaluate the same Nusselt number, NUD. So this is NUD as a function of x. Okay. So it's the same NUD that you have got here, but in a simplified expression, so that it can be evaluated more easily than the series solution that is here. Okay. Similar solutions, Levick solutions, are also available for constant wall flux case and also for simultaneously developing flows. So the last that I'm going to talk about is simultaneously developing flows. As I told you, for simultaneously developing flows, there is no analytical solution that is feasible. The equation is a partial differential equation, so no general analytical solutions. Is possible. So either use the solve specific cases using computational software and put them together, or you go to get them by experiment. Okay, so I'll just summarize some results which are available that can be used analytically, but the expressions are quite complex, as you can see. For example, when both simultaneously developing means both velocity profile and temperature profile are developing at the same time. So fluid mechanics solution, delta P divided by half rho u bar square, this is going to be equal to 13.74 into x. I'll write it as double tilde because this is a slightly different definition, to the power of half plus 1.25 plus 64 x double tilde minus 13.74 into x double tilde raised to the power of half, the whole thing divided by 1 plus 0.00021 x double tilde raised to the power of minus 2, where x double tilde is nothing but x by d divided by RED. Okay, there is no Prandtl number here, so it's an x double tilde. So this is the expression for the skin friction coefficient CF of x, okay, at different locations. So this is basically correlated from the solutions that are available either numerically or experimentally. Okay. Similarly, for constant wall temperature, so T wall is constant, then you get NUD is equal to 7.55 plus, so this is a fully developed value that might come, plus 0.024. You can see how complex the expression goes. X tilde raised to the power of minus 1.14 multiplied by 0.0179 into Prandtl raised to the power of 0.17 into x tilde raised to the power of minus 0.64 minus 0.14, the whole thing divided by 1 plus 0.0358 multiplied by Prandtl raised to the power of 0.17 into x tilde raised to the power of minus 0.64, the whole thing squared. Okay, so this is the expression for constant wall temperature, and this is compiled by Shah and Bhatti. R.K. Shah is a very well-known name in heat exchanger designs. So this is an expression compiled by Shah. For constant wall flux, the expression by Churchill and Ozo is more commonly used. This is again a more horrendous expression. NUD is equal to, so this x tilde is the usual one. X tilde is x by d divided by RADPR. Okay. This is equal to, okay, this is a little bit more complex than that. NUD divided by 4.364 multiplied by 1 plus grades number divided by 29.6, the whole square, the whole thing to the power of 1 by 6 is equal to, again a large expression, 1 plus grades divided by 29.06, 29.6, sorry, Let's start at 39.6. It's 19.04. Divided by 1 plus Prandtl divided by 0.0207 whole to the power of 2 by 3, and this bracket closes to the power of half. Another bracket opens. 1 plus grades divided by 29.6, the whole thing to the power of 2, the whole thing raised to 1 by 3. This whole thing is in bracket, and this raised to 3 by 2, and this whole square bracket is raised to 1 by 3. So this is the horrendous expression that I was actually talking about. So this is in some sense fitted to data where grades number, I can write it here, is going to be equal to pi by 4 x tilde. Okay, so x tilde is this, so grades number is pi by 4 x tilde, which is already something which we defined. So this basically is the kind of formula that you have derived. So you can see that it actually is not possible to analytically solve this problem. So the problem is either solved numerically or the data measured experimentally and correlated with the parameters that we are familiar with. Okay. So that is what I wanted to cover in the developing flows as the content. So I'll stop with this here. In the next 1 or 2 classes, we will cover turbulent internal flows. Okay, so all this while we have been looking at laminar internal flows. So we'll look at turbulent internal flows both for fully developed and for the developing regions, and that will conclude the topic on internal flows. So I'll stop here, and we'll continue with the next.